So let's get right on with our Test 1 review for Physics 2020. Now remember, this isn't meant to completely cover everything that's going to be on the test. This just summarizes really big ideas and equations that you'll need when you take your Test 1. To really study for the test, you should go back through, work problems, work problems, work problems. Okay? Alright, so here's some ideas about the test. This is going to cover chapters 1 and 2 in your textbook Purcell and Morin's Electricity and Magnetism 3rd edition. Please bring blank paper, pencil, and a calculator to the test. You might not have enough space to work everything on the test that I print out. You can bring a 3-inch by 5-inch index card as your own equation sheet. I will give the sheet with the list of the rectangular, cylindrical, and spherical coordinates and the relationships from differential calculus, so you'll have that. And I'll also give any necessary constants that you need, like the Coulomb constant, the permittivity of free space, the mass and charge of particles, and things like that. And as a reminder, this is just going to cover chapters 1 and 2. Okay, so the first big idea was about charge. We learned that charge is conserved. So for example, if you rub a balloon on your head, you can transfer charge from your head to the balloon or vice versa, but you're not going to create or destroy charge when you do that. Even if you are creating new particles, like you do in pair production, net charge is conserved. So for example, in pair production, you start off with a photon, which has no net charge, and then you create a particle-antiparticle pair, also having zero net charge when you add up the charges on all the particles involved. Charge is also quantized, and that means that any charge that you have, Q, you can express as an integer, here called n, times the fundamental charge. The fundamental charge is the charge that you would find in magnitude, of course, the absolute value of the charge that you would find on a proton or an electron. Protons are positively charged and have a charge of 1.602 times 10 to the minus 19 coulombs. And electrons have the same magnitude charge, but of course they're negative. The coulomb is the SI unit of charge, but it's a pretty large unit, so sometimes we find it handy to express charge in other units. Like in the CGS unit system, the electrostatic unit is the unit of charge, and 1 coulomb is 3 times 10 to the 9th electrostatic units. The first law that we're going to talk about is Coulomb's law. Like charges repel, and opposite charges attract. The strength with which they repel or attract is mathematically given by Coulomb's law, where the force is equal to the Coulomb constant K. The Coulomb constant is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. And that's equal to 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space, which is 8.854 times 10 to the minus 12 Coulomb squared per Newton meter squared. Okay, so the proportionality constant for the force is the Coulomb constant, and then for the rest of the magnitudes, the force is equal to or proportional to the product of the charges in question, so the two charges Q1 and Q2 that are attracting and repelling each other, those go in the numerator, and then divided by the distance between those charges squared, r squared. Now, as a reminder, we treat point charges like protons and electrons as point charges. We don't think about their extent when we do these Coulomb's law type equations. So yet again, the magnitude of the force is K Q1 Q2 over r squared, where r is the center to center distance for your charges. Now, this is of course a vector. Force is a vector. So the direction of the Coulomb's law force will be along the line connecting the centers of the two charges. And then of course, if they're like charges, they repel. So that means that the force lines would point away from one another, as shown here in the figure. If you have a positive and a negative charge, then it's an attractive force, and they point towards one another. Now remember, as always, that what you're going to do first in any of these Coulomb's law type problems is you're going to draw your free body diagrams for your charges in question and indicate the direction of the force by the direction of the arrow that you draw for the force, okay? Then you're going to calculate the magnitude, okay? Now remember, the magnitude of the force is the absolute value of that, so you're just calculating the length of that vector. You're not going to plug in minus signs for minus charges there, you're just going to calculate the magnitude. And then what you do is you use your free body diagram to figure out the direction of the force vector. That's when you would put in your plus and your minus signs. Remember, since force is a vector, the minus sign just indicates which way it points. So don't double count your minuses, okay? All right, also remember about your Coulomb's law force, that it's an action-reaction pair. So as shown here, the force from charge 2 on charge 1, shown here as F21, is opposite in direction but equal in magnitude to the force on charge 2 from charge 1, shown here as F12. And that will always be the case for this Coulomb's law force. It's part of an action-reaction pair. Another thing is that if you have more than 2 charges, that in order to get the total force on any one charge, you have to do the vector sum of any pairs that you might have. So for example, if you had 4 charges, then the force on charge 1 would be F21 plus F31 plus F41. And of course, if you had more than that, you just have to keep going. This is called superposition. Now let's talk about the electrical potential energy. Remember that the force is always equal to the minus gradient of the potential energy. And so we can write the potential energy equation as the negative integral of F dot ds for any particular force. That's no different here. So if, for example, we plug in the Coulomb's law force that we have from the previous slide, K Q1 Q2 over R squared, then what we would do is we would integrate that with respect to R, and that would give us our potential energy expression for the potential energy in between 2 point charges. That potential energy expression is U is equal to K, the Coulomb constant, times the product of the magnitude of the charges Q1, Q2 over the distance in between those charges, R12. Now here, the sign is important. Unlike in the force, in which case the sign just indicates which way the force points, the potential energy indicates if it's a negative potential energy, that they're attracted to one another, and if it's a positive potential energy, that they're repelled from one another. Okay? The potential energy here is the amount of energy that it would take to take the 2 charges together if they started from infinitely far apart to their current location or separation R12. Now, if you have multiple point charges, yet again it obeys superposition, and you would sum up the potential energy for all the pairs of charges. So here, for the system of charges, these 3 charges, you would have to find the potential energy between charge 1 and charge 2, between charge 1 and charge 3, and between charge 2 and charge 3 to find the potential energy of the system. Okay? Now remember, if the 2 charges are the same sign, the potential energy is positive, and work has to be done to bring the charges together. That's because they repel one another. If the 2 charges have opposite signs, they attract, and that means that the potential energy is negative, and you'd have to do work to keep the charges apart. If you have a lot of charges, writing out those summations can get really super tedious. So if you'd like to use the double summation notation, here it is. U is equal to 1/2 times the sum over J is equal to 1 to N, where N is the number of particles that you have, and then times the sum of K not equal to J, K Qj Qk over Rjk. Say that 5 times fast. The double sum notation means that you take J is equal to 1 and then sum over K from N equal to, or K equal to 2, 3, 4, all the way up to N. Okay? Then you go to J is equal to 2 and you sum over K 1, 3, 4, N. Okay? Now you're going to count some charges twice, right? You're going to count all the charges twice. And that's why there's a 1/2 out front of it when you write the double summation notation. All right, next idea, electric field. If you have charges, then what they do is they establish an electric field in the region of space surrounding them. So the charge that establishes the electric field we typically call the source charge. And then if you bring another charged object, which we usually consider to be teeny-weeny with respect to the source charge, or an infinitesimal test charge, then that charge will enter the electric field and have a force that acts on it. The force that acts on a test charge in the presence of an electric field is given by F is equal to Q, the charge, times E, the electric field. Electric field is a vector, and the direction of the electric field is defined as the same as the direction of the force that would happen to a positive test charge. A negative charge would move anti-parallel to E. So remember that positive charges move downstream on electric fields and negative charges move upstream. If you look at the equation F equals to QE, then you can see that the SI units of the electric field would be newtons per coulomb. An alternative expression is volts per meter. Since the force between two charges is F is equal to K Q1 Q2 over R squared, then the electric field from a point charge, source point charge, would be KQ over R squared. Now the electric field lines point radially outward from positive test charges. That's what the R hat unit vector there indicates. And of course they point radially inward towards negative point charges. If you have a bunch of point charges and you want to know what the electric field is like at a point due to this system of charges, then it obeys superposition, and you can sum it up, do a vector summation. Here, E would be equal to K times the sum over all your charges of Qi over Ri squared R hat. When you're drawing these systems, sometimes it's helpful to draw the electric field lines so that you get an intuitive feel for what it would be like before you start plugging and chugging numbers in. If you're going to do that, there's a few rules for drawing electric field lines. Remember that in order to correctly draw your field, you have to have an arrow which indicates the direction the electric field vector points, which remember is in the direction that a positive charge would move. So don't forget to put your arrowhead on, okay? Also remember that the density of lines, or the number of lines per unit area, indicates the strength of the field. So you can see that here in source A, the density of the electric field lines is higher than it is through B. So that means that the field is weaker at B than it was at A. We talked about the dipole an awful lot. So here's a picture of what the electric field from a dipole would look like. Remember that electric field lines start on positive charges and end on negative charges. Since in a dipole you have the same amount of plus Q as you have minus Q, then you've got the same number of field lines leaving the positive charge as landing on the negative charge. Okay? We talked about the dipole moment vector. The dipole moment vector is often symbolized with a P, and P is equal to Q times L, where Q is the charge on one of your charges, and L is the distance in between your positive and your negative charge. The dipole moment points in the direction that the electric field points in between the two charges. If you're finding the electric field from a continuous charge distribution, there's a couple of different ways to go about them. One way is Gauss's law, which we'll discuss later, but the other way is to directly integrate over the charge density and find what the field is like at some point, here labeled P. To do that, what you're going to do is divide the charge distribution into small little cubes, right? Each of those little cubes would contain an infinitesimal amount of charge, dq. And then you would calculate the electric field due to one of those infinitesimal cubes at point P. And then you would sum up over the entire range of your charge distribution, right? So you would sum over all your little dq's. Remember that when you make your dq's small enough and your source charge is continuous enough, then your summation becomes an integral. And so we can express for a continuous charge distribution the electric field at some point P is equal to K times the integral of dq over R squared in the R hat direction. Okay? Now dq is not usually what we integrate over. Usually we do spatial integrals. And so remember that you have to switch between your dq and your spatial coordinates using the idea of charge densities. A volume charge density is when a charge is distributed evenly through a volume. We oftentimes use the symbol rho for that, and rho here would be the charge divided by volume, and the units would be, of course, coulombs per meter cubed. Sometimes you have charge distributed over a surface. When it's distributed over a surface, we use sigma, and that is the charge divided by the area, and it would have units of coulombs per meter squared. And then if it's distributed over a line or a wire, then we often use lambda to symbolize the charge density, and lambda is equal to the charge per unit length, or Q over L, and it has units of coulombs per meter. Then what we would do is we would solve for dq in terms of either rho, sigma, or lambda. For a volume charge, dq would be rho dv. For a surface charge, dq would be sigma dA. And for a length element, dq would be lambda dl. Okay? Now, these different dv, dA, and dl could be written in terms of whatever coordinates are handy for the problem. So, for example, if you have a spherical charge density, then your dv might be r squared sine theta dr d theta d phi for your spherical coordinate differential unit. Remember that I would give you those things on a test, what the dv, dA, and dl would be in different coordinate systems. All right, next definition. If you don't want to do the integral over your continuous charge distribution, if there's an easier way to get around it, you might want to try Gauss's law. And to talk about Gauss's law, I first have to introduce the idea of flux. Electric flux is the product of the magnitude of the electric field and the surface area A perpendicular to that field. So if you have field flowing through some area, then the electric flux flowing through that area would be E dot A, where E is your electric field vector and A is your area vector. The area vector has the magnitude of the area of whatever surface you're looking at. And the area vector points normal to the surface. The units of electric flux are Newton meter squared per Coulomb, which I realize is kind of strange units. Now, for open surfaces, the area vector can point in either direction. But if you have a closed surface, your area vector is defined to point outward, okay? So here, the area vector can change direction over this weird shaped surface. Depending on where you are at the surface, you might be pointing in a different direction to point perpendicularly outward from your surface, for example. Here it's up and to the right, but if you were looking at the bottom of the shape, maybe it would be down and to the left, for example, is the direction that your area vector would point. Now, if you have a closed surface of arbitrary shape, then what you're really interested in probably is the net flux through the surface. And to do that, what you'd have to do is sum up over the entire surface using these little differential area elements and do the summation over all the differential area elements. Well, you can see where this is going. It's going to an integral. And so the net flux through a closed surface is the integral over that surface of E dot dA. Now, Gauss's law mathematically states that the net flux is equal to E dot dA. But Gauss realized something very important, that there wouldn't be any net flux through a surface if that surface didn't enclose some sort of charge. So the amount of flux that penetrates through a surface, the net flux, is going to be equal to the enclosed charge divided by epsilon naught, the permittivity of free space. Now, if you have a bunch of point charges enclosed by the surface, you can just sum up over all the point charges, get your total net charge, and then divide by epsilon naught. Note that you can be enclosing a lot of charge but not enclose net charge. If you have equal amounts of positive and negative charge that you're enclosing, you've got no net flux through that surface because net, you're neutral, okay? Now, if you have a continuous charge distribution, then rather than summing up over all your little dq's, that's going to go to an integral. And then your net flux, which is equal to the integral of E dot dA over the closed surface, is also equal to 1 over epsilon naught times the integral of rho dV. So you're going to integrate over your surface through the whole volume of your charge density. Okay? So this is Gauss's law. And in theory, it can be used to find the electric field for any charge configuration. But in practice, it's easier to use Gauss's law only if you have very symmetric distributions, like spheres or concentric spheres, or cylinders or concentric cylinders, or line charges, or planes. So those are the kinds of things that you typically use Gauss's law for. And remember that we went through all those simple geometries in class, and they're also in your book. So you should definitely review those for the test. So what you do is you apply Gauss's law by drawing yourself a little imaginary Gaussian surface. So you'll be given some shape, right? And it'll either be a sphere or a cylinder or a plane or a box or some simple shape with a high degree of symmetry. Then you can look at that and say, okay, my Gaussian surface is an imaginary surface. Doesn't necessarily correspond to the real surface, right? and I would draw my Gaussian surface to match the symmetry of my problem. So for a spherical problem, for example, my Gaussian surface would also be a sphere. What you want to do is you want to choose a Gaussian surface that satisfies these conditions. The electric field can be argued from symmetry to be constant over the surface. So for example, if you had a constant sphere of charge, right, you might, if you want to know the electric field inside, you might choose a Gaussian surface that's a sphere that's concentric with the other one. And remember to draw your imaginary Gaussian surface inside that other sphere, okay? So that's what you would do. Now, you also want to make sure that your dot product can be expressed as a simple algebraic product. So you want your electric field vector to be either parallel or perpendicular at all points to your area vector, okay? And that makes that integral over the closed surface of E dot dA very simple, okay? All right. Now, if you have a discontinuity in your electric field, and this can happen very easily, okay, say, for example, you have a spherical shell, for example, with a surface charge on the outer surface, then that can cause a discontinuity in the electric field. E-fields can be discontinuous at any place where there's an infinite volume charge density, like a point charge, a line charge, or a surface charge. And what happens is that causes a discontinuity in the electric field on either side of the distribution. The electric field can change direction abruptly or go from nothing to something. If that discontinuity occurs due to a surface charge, then the change in the electric field is always going to be the same. And it's always going to be sigma over epsilon naught. And remember that sigma here is your surface charge density, and epsilon naught is the permittivity of free space. Okay, let's talk about alternative expressions of Gauss's law. What I showed you before was the integral form. The net flux is equal to the integral over the surface of E dot dA, which is equal to the enclosed charge divided by epsilon naught. And the enclosed charge divided by epsilon naught is equal to either the summation over all the point charges, sum of Qi over epsilon naught, or a volume integral, 1 over epsilon naught integral rho dV. That's the integral form of Gauss's law. But remember that we can say generally from vector calculus that if you have an electric field, the integral of any kind of vector field dotted with the area vector, then that can be written as the triple integral of the del dot the field integrated over the volume. So that's just something that you usually learn in your third calculus class, okay, from vector calculus. And you can always write it that way. This is known as the divergence theorem, or sometimes Gauss's divergence theorem. Now, if you look at those two equations that I've written here, then you can see that you've got an integral over the volume for del dot E, and you have an integral over the volume for rho over epsilon naught. That means that we can equate those things. And so we end up with this expression, or the differential form of Gauss's law, which is del dot E is equal to rho over epsilon naught. Remember that del is your vector gradient. In Cartesian coordinates, that would be partial with respect to x, x hat, plus partial with respect to y, y hat, plus partial with respect to z, z hat. And you could express that in spherical coordinates or cylindrical coordinates, of course, and remember that I would give you those on the test. In words, Gauss's law says this, that in order to have a net field flux into or out of a closed surface, you're going to have a source of charge inside that surface. If there's no net charge inside the surface, then what goes in the surface is also going to come out of the surface, which is no net flux. Now, this source of charge that you have enclosed inside this surface, that causes your electric field to diverge. So that's what it means in words. Next idea. We also talked about the potential energy per unit charge, U over Q, or the electric potential. And sometimes I refer to this as voltage, just because students get a little confused about electric potential versus electric potential energy. Okay? Now, the potential is characteristic of only the field. Okay? The potential energy is characteristic of a charged field system. It includes information about the charge, but the electric potential or voltage does not. It just talks about the electric field. And in some ways that's a lot handier because you don't have to worry about what kind of charge you're putting into the field. So the potential difference here, or the change in voltage, is the meaningful quantity. The 0 point you can just kind of pick arbitrarily, and we'll talk more about why in a second. And for point charges and certain other charge distributions, for example like spheres, we take the 0 for the potential at infinity, okay? So if you're to write out an expression for the electric potential or voltage, we use, remember, phi, the Greek letter phi in this class. So phi is equal to U over Q, the potential energy per unit charge, which is equal to the negative line integral of E dot ds. We can also express the relationship between the electric field and the potential or voltage in this way, that the electric field is the negative gradient of the potential. Remember the gradient, partial phi with respect to x hat, plus partial phi with respect to y hat, plus partial phi with respect to z hat. Now, because the electric field and the potential are related by that derivative, any additive constant to the potential will result in the same electric field. And that's why it doesn't really matter where you choose your 0 point to be, and why it's important that the difference in potential be expressed, or the difference in voltage, and not the overall raw number. In that way, it's kind of like gravitational potential energy, right? Okay, so let's talk about energy, the direction of the electric field, the potential energy, and the voltage. So here we see in this figure an electric field that's directed downward. So our electric field points downward there. Now, since delta phi is equal to the negative integral of E dot ds, then what that would mean is that point B would be at a lower voltage or potential than point A. In other words, if you move downstream, you're moving to lower voltage. Now, if you have a positive test charge and it moves from A to B, then it's going to lose potential energy. So for example, if I placed a positive test charge at A, it would feel a force from that field downstream in the direction the electric field would point. That force would cause it to accelerate and it would gain kinetic energy. So, if there's no other forces to consider and you place a positive test charge in an electric field at rest, it'll move downstream, gaining potential energy, or gaining kinetic energy, losing potential energy, and losing voltage. Now, let's talk about what happens if it's a negative charge. If the negative charge goes from A to B, remember, the voltage or potential does not depend upon the charge itself. It just depends upon the field. So it's still going to lose voltage. But if you have a negative charge and you force it to move downstream, that's not the direction it wants to go. It wants to go upstream. So in order to force it downstream, you have to do work. And that's going to increase the potential energy if you move it downstream, if you force it to go downstream. Okay? Now, doing these kinds of problems, we had some where we placed point charges in fields and we watched how they move. Remember that if you have a change in potential energy, then you can use that in conservation of energy. If there's no other dissipative forces or no other forces to consider, then you can say that any potential energy that's gained or lost is then going to be lost or gained by the kinetic energy. So you can use conservation of energy to solve these kinds of problems. All right, so the potential for a point charge, or the voltage for a point charge, phi, is equal to kq over r. Remember, k here's the Coulomb constant, q would be the magnitude of the charge, and r would be the distance from the point in question to the charge. So if you wanted to know what the potential was like some distance r away from a point charge, this is the formula that you would use. It obeys superposition, so if you have a system of charges, then you wanted to know what the potential or voltage was like at a point due to the system, then what you would do is the sum of kq over r, where r is the distance from the point in question to each charge in turn, and q is the value of each charge in turn. When you use this expression, whether you know it or not, you're taking the potential to be 0 at infinity. So if you get infinitely far away from a point charge, there's no effects. If you have a continuous distribution of charge and not point charges, then what you do to find the potential is you do the integral of rho dV over 4 pi epsilon naught r, okay? And you do that summing over all the little dq's just like you did for your electric field. So we have a couple of different options here. Depending on the symmetry of your continuous charge distribution, it may be easier to use Gauss's law to calculate the electric field, right? and then integrate that field if you need the potential. That might be easier, because if you have a very symmetric distribution, the application of Gauss's law can be quite straightforward and simple to do. Now, if you have a more complex charge distribution that doesn't have a simple symmetry, then it may be easier to find the potential using this formula and then differentiate to find your electric field. Okay? So it just depends. You can look at your charge distribution, identify certain symmetries that you might see, and pick one or another. And we've done this a lot in class, and you've done it a lot for your homework, so you should have plenty of examples to look over to study this. Okay, last push. We've got all these expressions now that relate the charge distribution to the electric field to the potential. So let's kind of pull them together. Remember that the electric field is the minus gradient of the potential, right? Minus grad potential. Now, if you combine that with the differential form of Gauss's law, del dot E is equal to rho over epsilon naught, plugging in for E, then you get del dot minus grad phi is equal to minus grad squared phi over, which is equal to rho over epsilon naught. Now this minus grad squared phi is equal to rho over epsilon naught. That's called Poisson's equation, and is a direct relationship between your potential or voltage and your charge distribution rho. Now the del squared, that's called the Laplacian, and the Laplacian is, in Cartesian coordinates anyway, partial squared with respect to x squared plus partial squared with respect to y squared plus partial squared with respect to z squared. Now remember, on the test I'll give you the gradient operator, the Laplacian, and all that kind of stuff that you might need in spherical or cylindrical coordinates. So now we come to this really handy figure from your textbook, Purcell and Morin's Electricity and Magnetism 3rd edition. In this figure, they show you all the ways to get between the electric field, which is up top here, the electric potential, lower right corner, and the charge density rho. So you have the ways to go back and forth here. Make sure that you're familiar with solving for all of those things, okay? So if, for example, you're going from the electric field to rho and back and forth, then you can use Gauss's law, rho over epsilon naught is equal to del dot E, or you can integrate over rho to find the electric field, okay? And then to get from the potential to the electric field, E is minus grad phi, or phi is the negative line integral E dot ds. To get between the charge and the potential, you've got a direct integration that you can do to find the potential from the charge. Phi is equal to 1 over 4 pi epsilon naught, integral of rho dV over r, or you can use the Laplacian and use Poisson's equation. Rho over epsilon naught is negative grad squared phi. Okay, so there's all those ways to get back and forth. And finally, we talked about other ways to calculate the potential energy. Remember that any energy that's stored is stored in the form of an electric field. And so your equation here for the potential energy in terms of the electric field is U is equal to epsilon naught over 2 times the integral of E squared dV. So if you know what your electric field expression is, then you can integrate the square of the field over the volume to find the stored potential energy. There's also this expression. U is equal to 1/2 times the integral of rho phi dV. So if you know your charge distribution rho and your potential phi, then you can integrate that and divide by 2 to get your potential energy. Okay, so that's the tobacco auctioneer's version of chapters 1 and 2. Remember, there's plenty of examples in the book, in the notes, and in your homework for you to look at. Remember, the best way to study physics is to work problems, work problems, work problems, work problems. Okay? So do it. And good luck on your test, and I'll see you soon.